components to start and keeps track of them when they're over with their transform or computation. And also it controls the microprocessor and asks it to start post-processing the data once it's over. And in the hybrid implementation for NVDR, we used the main control was written in custom PHDL, the ADC driver, custom HDL, and the frequency detection, and FFT core was using Xilinx cores. The NVDR DOA was implemented in the microblaze, as I mentioned before, because it's faster to implement. And then the results are stored in a Xilinx core generated memory. So, in our, before doing the NVDR estimation, we needed to do some optimization on the hardware that have been designed for Bartlett. So a pipeline architecture was introduced. So sampling and FFT are overlapping. Once the first sampling process is over, FFT starts, and then once the sample data are loaded into the internal memory of the FFT, the sampler is triggered again to acquire new samples and store them into the memory. Also, the frequency detection is only runs only one time over one channel, and then it's skipped over the rest of the averages. Here it shows a snapshot from the external logic analyzer that shows how the signals generated. The main thing here is that we see the sampler once the first sampling is done, like FFT is started, and then before it's done, once the data is loaded, we start a new sampling process again. And then, so this way we have the FFT and the sampling overlap. So for the microprocessor, after performing the FFTs, the soft processor will perform the rest of the calculations. So it loads the data, computes the covariance matrix, and then calculates the inverse of the covariance matrix using the Gauss-Jordan elimination. I was found in one publication that it was actually gives comparable results to other techniques for an 8-element antenna array. So because the covariance matrix is 8 by 8, and for such a small matrix, they found that the time is comparable to other techniques. And then finally, we compute the power spectrum and take the estimated DOA. And here we show some results exported from the FPGA. That's using one signal coming at 90 degrees. And we see here the peak at 90 degrees. And also for two signals, we have at 90 degrees and at 260 coming to the FPGA.
Was this a 5/8 down converted or off the generator array?
It was off the generators.
Okay.
Yeah, all the results that we're showing, systems still haven't been integrated with the whole picture.
Okay.
So the hybrid system are the results. It takes to complete all the FFTs, the 128 rounds, 7.8 milliseconds. To compute the covariance matrix takes it 37 milliseconds. For the inverse of the covariance matrix needs 5 milliseconds or 6 milliseconds, and then 100 and 130 for power and calculate the normalized power. Also, the weights in this case were calculated in the microblaze. The reason of that is because we wanted to have high resolution and have a matrix that covers 360 degrees. So it's going to be huge to fit in the microblaze. So we had to do the calculation. We had to do the calculation on the fly, but actually it might be good.
Thank you, Windows.
It might be actually good to store the weights in memory on the FPGA, and then load it once the hardware loads up, and then use it in the calculations. This way, a long latency will be optimized.
What is hardware is normalized power?
Well, the reason it's done here is just to, when I exported it, just looks nice. And
Yeah,
so it's not really necessary. This is another one that, yeah, the main thing is calculating the power and then detect the piece from that one.
Do we have a plan to implement all the segment part PTA?
Which all hardware?
Because I really don't like a microphone.
Yeah. Well, and this is the resource utilization. It's, yeah. So in order to look at how a system would perform on using custom HDL or hardware, the only or the main optimization that we can make here, other than knowing that the hardware will perform faster, is that we can pipeline the computation of the covariance matrix. So by figuring out a way to process the data as they are generated through the FFTs. So some considerations were taken. So we have pipeline sampling in FFT. FFT has a long latency, so if we can hide some of the computations of the covariance matrix in that latency, we can save a lot of time for processing. Also, we have limited FPGA resources, so we need to figure out how to do the covariance matrix. Looked at systolic array implementations in order to do matrix multiplication. Basically, to describe systolic arrays quickly, it just takes two matrices and cycle them through, and then performs the multiplications as they are going. So it has a linear order of magnitude rather than I think for matrix multiplication, if you want to do it in a soft processor, it might be quad or maybe like squared or something. So, but the systolic array is usually done by implementing, for example, for an 8x8 matrix, you need 64 multipliers, which is a lot of resources that we don't have that much resources. So we use only one multiplier, figure out an algorithm how to do that, how to use only one multiplier to perform all the computations. And then we store the input matrix in one memory block only, and then we figure out the transpose on the fly using different addressing techniques. So instead of storing two memories, we just use one memory and then have a different addressing scheme to load the transpose. So the block diagram for how I designed the hardware implementation for the R matrix computation. One multiplier here, that's the memory we're loading the FFT data from. This state machine controls all the parts, generates the correct addresses to load the right address for both the X matrix and the transpose. This is the actual DMUX, this is the multiplier. So the multiplexer picks which decides the data we're loading from the memory. Is it the transpose or the actual matrix? And then the results are stored in the memory. So looking at performance of the system, we actually, without pipelining the covariance matrix, the covariance matrix is calculated in 580 microseconds. With pipelining, we only need an additional 16 microseconds after the last shot of FFT to complete the computation. And here, comparing it with the hybrid system, so pipelined architecture is 2,300 times faster. Without pipelining, it's 64 times faster. So I'm going to look at this results and compare and try to look at the complete system and see how would it operate if it's all implemented in hardware. The only thing here I need to mention is that only the covariance matrix can be pipelined, because in order to compute the power, we need to have the covariance matrix completely computed, because and then for calculate the power, because in the process of calculating the covariance matrix, we don't only come up with the first sets of results and then go to the next set. No, it's more like calculating all the results and accumulating until we reach the final